Today we're going to go over the second part of the electrochemistry, and as I was looking at the slides, it seemed to me fairly likely that we could probably get this done in one episode, but we'll see how it goes. This is probably the most difficult aspect of the electrochemistry material, and that is the Nernst equation. And what this triangle attempts to show is that there is a direct relationship, a calculable relationship between the equilibrium constant shown at the top of the triangle, the Gibbs free energy at baseline, and the baseline electrical voltage that can be detected. And these three entities are related to each other. And if you have any one of these, you can calculate the other two. So for example, if you know the equilibrium constant for a process, you can use this equation, minus RT natural log of K, to calculate the Gibbs free energy. R is the same R that we have spoken about in the past. T is the temperature in Kelvin, and so you can use those two properties or those two measurements along with the equilibrium constant in order to find delta G. Now obviously the delta G involved is the delta G that is associated with the temperature at which the equilibrium constant is measured. So the temperature that the equilibrium constant is measured is the temperature that needs to be used in the equation, and it will be the delta G finding for that temperature. And so that's the first relationship. The second is here. If you know the equilibrium constant, you can also calculate the voltage of the cell. And the relationship there has to do with two new quantities. First of this is the term F, which stands for Faraday's constant. Faraday's constant is something I'll show you in just a minute. And then this little n, and the little n has to do with the number of electrons that are transferred in the process. You will recall that when we did the various calculations in class, there were 3 electrons or 4 electrons or 2 electrons or 6 electrons. So whatever number of electrons is involved in that is transferred in the process, that number is what you put in for n. And so you put Faraday's constant and that number, again R and T are the same R and T, and then the natural log of the equilibrium constant, and you can calculate again the cell voltage, the baseline cell voltage. The third is at the bottom here, and if you know the cell voltage, you can use Faraday's constant and N again to calculate delta G. So as I said, given any one of these three quantities, you can calculate the other two through these various equations. So Faraday's constant, as I said, I was going to tell you what Faraday's constant was, and Faraday's constant is 9.648 times 10 to the 4th coulombs per mole, or joules per volt mole. The charge of a mole of electrons, that's why N has to be in terms of the number of electrons that is transferred. So we're talking about moles of electrons as opposed to other types of moles. The Nernst equation is that the electrical voltage of any cell is equal to the baseline electrical voltage corrected by this factor that's shown here, and that is RT over NF times the natural log of the equilibrium quotient at whatever situation you're in at the time. It's not the same as the equilibrium constant. If you recall back when we were doing equilibriums, the equilibrium quotient is the situation at the moment. And if you're at 25 degrees, then you can simplify RT N over F into one number, 0.0257 times divided by N times the natural log of Q. So 0.0257 just represents RT divided by F. R being a constant, F being a constant, and we've set T at 25 degrees or 298.15. If you do that math in advance, it gives you 0.0257, and then all you have to do is divide that by the number of moles of electrons that are involved, and then multiply by the natural log of Q. So these are the two equations that you can keep in mind. Actually, you can keep in mind the one on the left here, because the one on the right is simply a simplification of the one on the left if you assume 25 degrees. So if you don't want to memorize that, you can just remember the one on the left and then put those numbers in. So let's take a look at a couple of calculations based on these findings. And as I said, if you know any one of the following three constants, then you can calculate the other two. And so this problem says, what is the delta G0 and equilibrium constant for the following? And it shows a reaction, and you're thinking, well, I don't have any. Well, remember, if you specify 25 degrees, you can look up various things in the back of the book under table L and figure out what E0 is. And so that's what we'll do first. If you go to Appendix L, let's put in our arrows here. If you go to Appendix L, you can look up the iron to iron 2 plus 2 electrons, and that's the oxidation. And so remember what's in the table is all reductions. And so this one is the opposite sign of what's in the table. And you have minus 0.447. Then you take 2 times the silver electrode, and the silver electrode is a reduction, and it's 0.8. And you use those two, you subtract, or you add those two together, and you end up with 1.247 volts as your voltage. And so you now have the voltage at 0 at this for this reaction. So now you can find the equilibrium constant and the delta G0. So the first equation is what I put right here, is that E0 of the cell is equal to RT over NF times the natural log of the equilibrium constant. At 25 degrees, RT over F simplifies to 0.057 divided by N. N is equal to 2 because you're transferring 2 electrons with this equation. So if you put 2 in there, that means that that 1.247, which is the cell voltage, is equal to 0.0257 over 2 times the natural log of K. So the natural log of K will be 2 times this voltage divided by 0.0257. If you do the math, you find out that the equilibrium constant is 1.3 times 10 to the 42. And then delta G is equal to NF E0. N is 2 again, minus NF E0. N is 2 again. Faraday's constant is 9.649 times 10 to the 4th. And the E0 is 1.247. Again, if you do the math here, you get 2.406 times 10 to the 6th joules per mole, or minus 240.6 kilojoules per mole. So this is a spontaneous reaction, obviously, both from the voltage perspective and from the delta G perspective. So let's look at another problem, and let's take into account the concentrations of some of these values because it's important. Well, I'll show you why that's important in just a second. So we've got solid cobalt plus iron 2+, and the iron 2+ concentration is 1.94 molar, goes to cobalt, and it's 0.15 molar plus iron solid. And you see that from the table, you have first the oxidation of cobalt, which is minus 0.28, and the reduction of iron, which is minus 0.447. And so E0 is going to equal minus 447 minus a minus 28, or minus 0.173. Now the negative sign here means that this is not a spontaneous reaction. But the E0 is at equilibrium, not at these concentrations. So you have to calculate Q at this point, and Q is going to be the product, which is the cobalt, 0.15, divided by the reactant, which is the concentration of the iron, and so Q is 0.077. So the new E is equal to E0 minus, and since we're at room temperature, that's 25 degrees, so we can use the 0.0257 divided by N times the natural log of Q. N here is going to be 2 because it's 2 moles of electrons are used. And the natural log of Q is the natural log of 0.077. So if you put those numbers in, you get a new value for this cell, which is corrected for the different concentrations, and you end up with 0.014 volts, minus 0.014 volts. It's still not spontaneous. So those are the two types of problems you will see potentially on a quiz or test. One is like this, where you are given one of the three values at 25 degrees or at some state, and you have to calculate the other two. And the other is this situation where you're given the concentrations, and you have to calculate both E0 and then the new E based on the different concentrations of the electrolytes, and see how much it changes this cell voltage and whether the different electrolytes can actually take a negative or a non-spontaneous and turn it into a spontaneous situation.